A planetary system is a set of gravitationally bound, non-stellar objects in orbit around a star or star system. Generally speaking, systems with one or more planets constitute a planetary system, although such systems may also consist of bodies such as dwarf planets, asteroids, natural satellites, meteoroids, comets, planetesimals and circumstellar disks. The Sun, together with its planetary system, which includes Earth, is known as the Solar System. The term exoplanetary system is sometimes used in reference to other planetary systems. A total of 2047 exoplanets have been identified as of 12 January 2016. Of particular interest to astrobiology is the habitable zone of planetary systems where planets could have surface liquid water. History. Heliocentrism. Historically, heliocentrism was opposed to geocentrism. The notion of a heliocentric solar system, with the Sun at the center, is possibly first suggested in the Vedic literature of ancient India, which often refer to Sun as the center of spheres. Some interpret Aryabhata's writings in Aryabhatiya as implicitly heliocentric. The idea was first proposed in Western philosophy and Greek astronomy as early as the 3rd century BC by Aristarchus of Samos, but had received no support from most other ancient astronomers. Discovery of the solar system. De Revolutionibus Orbium Coelestium by Nicolas Copernicus, published in 1543, was the first mathematically predictive heliocentric model of a planetary system. 17th century successors Galileo Galilei, Johannes Kepler, and Isaac Newton developed an understanding of physics which led to the gradual acceptance of the idea that the Earth moves round the Sun, and that the planets are governed by the same physical laws that governed the Earth. Speculation on extrasolar planetary systems. In the 16th century, the Italian philosopher Giordano Bruno, an early supporter of the Copernican theory that the Earth and other planets orbit the Sun, put forward the view that the fixed stars are similar to the Sun and are likewise accompanied by planets. He was burned at the stake for his ideas by the Roman Inquisition. In the 18th century, the same possibility was mentioned by Isaac Newton in the General Scholium that concludes his Principia. Making a comparison to the Sun's planets, he wrote, "And if the fixed stars are the centers of similar systems, they will all be constructed according to a similar design and subject to the dominion of one." His theories gained traction through the 19th and 20th centuries despite a lack of supporting evidence. Long before their confirmation by astronomers, conjecture on the nature of planetary systems had been a focus of the search for extraterrestrial intelligence and has been a prevalent theme in fiction, particularly science fiction. Detection of exoplanets. The first confirmed detection of an exoplanet was in 1992, with the discovery of several terrestrial mass planets orbiting the pulsar PSR B1257+12. The first confirmed detection of exoplanets of a main sequence star was made in 1995, when a giant planet, 51 Pegasi b, was found in a 4-day orbit around the nearby G-type star 51 Pegasi. The frequency of detections has increased since then, particularly through advancements in methods of detecting extrasolar planets and dedicated planet-finding programs such as the Kepler mission, Origin and Evolution. Planetary systems come from protoplanetary disks that form around stars as part of the process of star formation. During formation of a system, much material is gravitationally scattered into far-flung orbits, and some planets are ejected completely from the system, becoming rogue planets. Evolved systems. High-mass stars. Planets orbiting pulsars have been discovered, and pulsars are the remnants of the supernova explosions of high-mass stars. A planetary system that existed before the supernova would likely be mostly destroyed. Planets would either evaporate, be pushed off of their orbits by the masses of gas from the exploding star, or the sudden loss of most of the mass of the central star would see them escape the gravitational hold of the star. or in some cases the supernova would kick the pulsar itself out of the system at high velocity, so any planets that had survived the explosion would be left behind as free-floating objects. Planets found around pulsars may have formed as a result of pre-existing stellar companions that were almost entirely evaporated by the supernova blast, leaving behind planet-sized bodies. Alternatively, planets may form in an accretion disk of fallback matter surrounding a pulsar. Fallback disks of matter that failed to escape orbit during a supernova may also form planets around black holes. Lower mass stars: as stars evolve and turn into red giants, asymptotic giant branch stars and planetary nebulae, they engulf the inner planets, evaporating or partially evaporating them depending on how massive they are. As the star loses mass, planets that are not engulfed move further out from the star. If an evolved star is in a binary or multiple system, then the mass it loses can transfer to another star, creating new protoplanetary disks and second and third generation planets which may differ in composition from the original planets, which may also be affected by the mass transfer. Planets in evolved binary systems. Haggai B. Peretz, the 13th of January 2011. Can planets survive stellar evolution? Eva Villiver, Mario Livia, February 2007. The Orbital Evolution of Gas Giant Planets Around Giant Stars. Eva Villiver, Mario Livia, the 13th of October 2009. Foretellings of Ragnarök, World Engulfing Asymptotic Giants and the Inheritance of White Dwarfs. Alexander James Mustel, Eva Villiver, the 5th of December 2012. System architecture. The Solar System consists of an inner region of small rocky planets and outer region of large gas giants. However, other planetary systems can have quite different architectures. Many systems with a hot Jupiter gas giant very close to the star have been found. Theories, such as planetary migration or scattering, have been proposed for the formation of large planets close to their parent stars. At present, few systems have been found to be analogous to the Solar System with terrestrial planets close to the parent star. More commonly, systems consisting of multiple super-Earths have been detected. Orbital properties. Unlike the Solar System, which has orbits that are nearly circular, many of the known planetary systems display much higher orbital eccentricity. An example of such a system is 16 Cygni. Mutual inclination. The mutual inclination between two planets is the angle between their orbital planes. Many compact systems with multiple close-in planets interior to the equivalent orbit of Venus are expected to have very low mutual inclinations, so the system would be even flatter than the Solar System. Captured planets could be captured into any arbitrary angle to the rest of the system. The only system where mutual inclinations have actually been measured is the Upsilon Andromeda system. The planets, C and D, have a mutual inclination of about 30 degrees. Orbital dynamics. Planetary systems can be categorized according to their orbital dynamics: is resonant, non-resonant, interacting, hierarchical, or some combination of these. In resonant systems, the orbital periods of the planets are in integer ratios. The Kepler 223 system contains 4 planets in an 8-6-4-3 orbital resonance. Giant planets are found in mean motion resonances more often than smaller planets. In interacting systems, the planets' orbits are close enough together that they perturb the orbital parameters. The Solar System could be described as weakly interacting. In strongly interacting systems, Kepler's laws do not hold. In hierarchical systems, the planets are arranged so that the system can be gravitationally considered as a nested system of two bodies, e.g., in a star with a close-in hot Jupiter with another gas giant much further out. The star and hot Jupiter form a pair that appears as a single object to another planet that is far enough out. Other, as yet unobserved, orbital possibilities include double planets, various co-orbital planets such as quasi-satellites, trojans and exchange orbits, and interlocking orbits maintained by precessing orbital planes. Extrasolar binary planets I. Formation by tidal capture during planet-planet scattering. Okurai, Nagasawa, Ida, 26 June 2014. Disruption of co-orbital planetary resonances during gas-driven orbital migration. Arno Perens, Sean Raymond, 19 May 2014. Captured planets. Free-floating planets in open clusters have similar velocities to the stars and so can be recaptured. They are typically captured into wide orbits between 100 and 105 astronomical units. The capture efficiency decreases with increasing cluster size, and for a given cluster size it increases with the host primary mass. It is almost independent of the planetary mass. Single and multiple planets could be captured into arbitrary unaligned orbits, non-coplanar with each other or with the stellar host spin, or pre-existing planetary system. Some planet-host metallicity correlation may still exist due to the common origin of the stars from the same cluster. Planets would be unlikely to be captured around neutron stars because these are likely to be ejected from the cluster by a pulsar kick when they form. Planets could even be captured around other planets to form free-floating planet binaries. After the cluster has dispersed, some of the captured planets with orbits larger than 106 astronomical units would be slowly disrupted by the galactic tide and likely become free-floating again through encounters with other field stars or giant molecular clouds. Number of planets, relative parameters and spacings on the relative sizes of planets within Kepler multiple candidate systems. David R. Chardy al. 9 December 2012. The Kepler dichotomy among the M dwarfs. Half of systems contain 5 or more coplanar planets. Sarah Ballard, John Asher Johnson, 15 October 2014. Exoplanet predictions based on the generalized Titius-Bode relation. Timothy Boved, Charles H. Lineweaver, 1 August 2013. The Solar System and the Exoplanet Orbital Eccentricity, Multiplicity Relation. Mary Ann Limbach, Edwin L. Turner, 9 April 2014. The Period Ratio Distribution of Kepler's Candidate Multiplanet Systems. Jason H. Steffin, Jason A. Huang, the 11th of September 2014. A Planetary System's Filter Capacity, a study based on Kepler results. Julia Fang, Jean-Luc Margot, the 28th of February 2013.